Hello, this is Lina Wiggins at Rutgers University in February 2012, and we're going to be talking in this video about three of the models that look at population change up to some limit with a couple of variations in the shapes of the curves up to those limits. Or in fact, we could do down to a limit as well. In the modified exponential, which is the first one we're going to look at, the capacity term C is typically given. In other words, it could be from some build-out analysis that takes the community out and uses up all of its legally zoned capacity, or to the limit of some infrastructure, water or sewer, or it could be a planned capacity from a comprehensive planning exercise. Here's the equation for the modified exponential. And by using some algebra and some log rules, then we can transform it, as it is here in the bottom, into a linear equation. Notice that here the x remains the same, but on the left-hand side, the y term is going to be transformed by a differencing here from the capacity and then a log transform. So let's look at that in a spreadsheet form. I haven't made this fancy. I'm going to leave you some of the work to do. This is for Middlesex County. I've chosen only 1940 to 2000. I would then project to 2010 and check it against the actual census decennial 2010 results. It's a good check of my model. Now I did have to do some transforms, and the first thing I had to do is look at the capacity at 900,000, which we used as a limit in another one of the templates. And here I'm going to take that capacity, absolute address B13, subtract the y value, and then if you remember that equation, it was the log of that difference. So now I'm going to take this as my x and this transform as my y, and I'm going to run a linear model. It's down here, and I made my decimal places up to 10 again. You need to carry your decimal places when you're doing these models. So now I have a linear model. I've got an estimate for A and an estimate for B, my intercept and my slope. And I probably would like to get my original model back. So I'm going to go and take the antilogs of A and B. So here's the antilog of the A parameter, and here's an antilog of the B estimated parameter. And then I can go back up here and use my original equation and plug in now my antilogged A and B, and I'll get my y estimates here. And then I can go ahead and plot them over in this graph, and I'm not going to make it fancy, but you can put the original series in. Looks like it has a pretty good fit, actually. 97% of the variation explained. Now we're going to look at the logistic curve, famous growth curve, S-shaped curve, and it has upper and lower bounds. Here is the equation. Notice on the left-hand side we have the reciprocal of y, and on the right-hand side it looks very similar to the modified exponential. So in this case, the ratio of the successive reciprocals of the y values would be a constant if we were doing at the coefficient of variation. Here again, we've got the growth here up to 1 over c. And our linear transformation looks more complicated, but in fact, it's not really that different. It's, again, got this b parameter, the a parameter estimates, and on the left side, we'll have to do the difference and then take the log again. So let's look at that one in the spreadsheet. So I've done exactly the same kinds of steps. I have x and y, my original values. Here I've done the reciprocal of y, which we saw we needed from that equation. Then the difference from the capacity number. In this case, it is the reciprocal of capacity. Then my log. Then exactly the same way again, I run my linear model and make my decimal places up. This one has about a 96% variation explained. Again, I take my anti-logs over here. So this is the anti-log of the A coefficient estimate, and this is the anti-log of the B coefficient estimate. Go up here, I'm just repeating the x values, make it a little easier. Then the log. Then here's my equation for my curve here. And then I've got my reciprocal. And that's my final y estimates. And they're pretty close, actually. We see this kind of movement up here. It's just sort of a barely curving S-curve. And again, you can complete my graph by adding the original data. Gompertz is a little bit more again. It's a curve. Look at these dates way back in the 19th century. We've got something that looks similar to the logistic and exponential, modified exponential curves. A little more complicated to do the transform for this formula, but again, we're just using our laws here. Finally, we get a transform curve that again is inherently linear. And here we'll see again we need x, does not need a transform. The y side, quite a complicated transform, the logs and then the log of the logs. But again, not that tough. So we go back to Excel, and you can see that I've done the log terms here, log of the population, and the log of the capacity. This is the log of the difference. That's my y transform. Once again, it's a linear model now. Run my linear model. This fits even just a tiny bit better. Get my A, get my B. And in this case, doing the transform back to that original equation is a little bit of a bear in Excel. So I'm going to bless you to just use the equation for the linear transform for this if it happens to be the model that you select.